Thank you. Hello, hello. Can you hear me? Oh, yeah. Thank you for cutting my biography in half. It was quite long. So, hello everyone, I'm Gerardo Viviers, and as Rob said, I work for the Learning and Development team at the RIPE NCC. Now, this presentation was made by two of my colleagues, Emile Ben and Alan Davies, so I have to thank them for making it. And that's also a disclaimer, any errors is not my fault. So we're going to be talking about some noteworthy cable disruptions in the Baltic Sea that happened end of last year and beginning of this year. And we're going to examine what we learned through doing some RIPE Atlas measurements. So we're not going to be talking about the causes of these cuts, but just what happened with the internet around them. Clicker. Yeah. By the way, those cable disruptions, I have nothing to do with them. That were happening here? No, not me. Now, this timeline shows a series of cable issues that we've been observing. The first one started on 17th November 2024, so last year, when the BSC East-West link was damaged, and that was followed by the Sea Lion 1, which broke just the day after. Actually, just some hours after. Both were repaired by late November, but the Sea Lion 1 had, again, problems on the 25th of December, some kind of Christmas present. It was repaired again on the 6th January, and then the LVRTC cable, which connects, I think it's Lithuania and Sweden, or Latvia, yes, was broken on the 26th of January. So while this might look like a catalog of mishaps, actually they yielded a lot of valuable data to understand how the internet operates. Now, the media coverage surrounding these events escalated quite quickly, with theories ranging from sabotage to undersea espionage, and I heard during lunch another theory. So there's a lot of theories, but there's nothing actually proven yet. So while such headlines might catch our attention, we're not going to go into them. We're just going to look at what the measurements revealed to us. Now, if you don't know, RIPE Atlas is a global measurement platform made up of more than 13,000 probes and around 800 anchors. Anchors are bigger probes that are able to do much more heavier measurements. Each anchor is capable of running continuous tests, such as ping and traceroute amongst the different anchors, and they're distributed worldwide. So you can think of them as a collective of small observers that can see every inch of the highway in real time and share the information with us. So our anchors form what's called a mesh, or what we call a mesh. Each anchor pings every other anchor every 4 minutes. And this allows us to track latency, packet loss, and other metrics. In essence, if something is unusual is happening, then, for example, like a sudden detour in connectivity, some changes on the network, then this mesh will detect it. It's somewhat like having eyes on every segment of the road, like we said. On 17 November, the first look that we did, the BSC East-West link, which connects Sweden and Lithuania, encountered issues. And on 18 November, the Sea Lion 1 link, which connects Germany and Finland, followed afterwards. We had about 100 anchors in Germany, 15 in Sweden, 12 in Finland, and 5 in Lithuania, and this provided ample vantage points from which we could observe these changes in the network. By focusing on data that happened around 8 UTC on the 17th, when the first break happened, and 2 o'clock UTC on the 18th, then we could pinpoint changes in latency and route adjustments. And here comes the nice statistics and diagrams. So this graph reflects the latency for the BSC East-West cable over a 12-hour window before and after the break. To highlight the shifts, each path's minimum latency is subtracted from its observed latency. So this makes it easier to see how certain routes slow down after the break. It's similar to tracking your usual commute time and then suddenly noting exactly when you had to take the scenic route to get to your destination. By digging deeper into the BSC east-west break, we found that about 80% of the paths showed no significant difference in latency, while 20% experienced an increased latency. The 10% of paths with the most severe impact saw increases of 10 to 20 milliseconds. So although 10 milliseconds won't ruin your cat videos, it does indicate the internet took a slightly longer journey to reach the destinations. It's a small but clear sign of rerouting at play. What's particularly interesting is that we didn't observe any significant increase in packet loss at the time of the cable break. So here we see no major shift in packet loss, which remained at 0% with minor spikes. Now, the timing suggests that despite physical damage, traffic simply found other routes. And turning to the Sea Lion 1, we note a significant latency shift a bit after 2 UTC on the 18th of November. So again, we subtracted the minimum latency to highlight the jump. And this illustrates how certain paths changed at precisely the reported time of the incident. This confirms once again that a portion of the traffic was rerouted. In the hour surrounding 2 UTC, 70% of paths stayed consistent, while 30% rose in latency. And about 20% of those saw an increase over 5 milliseconds. And although that increment is modest, it clearly aligns with the moment the cable was damaged and demonstrates that some traffic took a detour. Here we're going to look at the packet loss, and the baseline packet loss here hovered between 0.5% and 1%. And we see no major peak right at 2 UTC when the break happened. A separate spike, you can see, happened later, but it didn't correlate with the break. So we see this as an indication that it was an unrelated event. Apparently somebody was trying to download the whole internet and caused this problem. So once again, no large-scale meltdown, just some more evidence of effective rerouting. So what does this all actually tell us? There was a relatively minor but visible shift in latency for around 20 to 30% of paths between observed anchors. This shift allows us to pinpoint the precise time at which the damage occurred. The key finding, though, is that there was no concurrent increase in packet loss. And the internet effectively routed around the damage, finding alternative paths to deliver traffic. Sort of like your GPS when you're driving around and all of a sudden you find roadblocks and then it just finds a different way to get to the same place. Well, you get there. We did take, cable's being broken. We did take a deeper dive, so we initially relied on ping measurements, which provide a good end-to-end view, but we went a step further using trace routes to pinpoint how traffic was rerouted hop by hop. And this helps us to confirm whether the path changes occurred within networks, among different providers, or somewhere else. Now, each result adds a missing puzzle piece. For this deeper analysis, we looked at 3 levels of network resilience. So first, the inter-domain rerouting, where traffic is rerouted through alternative autonomous systems. Okay, we're rerouting, right? Stable. Where traffic is rerouted through alternative autonomous systems or internet exchange points using the eBGP protocol. Second, intra-domain rerouting, where rerouting happens within the networks along alternative paths using internal gateway protocols like OSPF or SIS. And third, circuit-level rerouting, where traffic is rerouted along alternative circuit-level connections between routers that share the same IP address. Each level is going to represent a different layer of the internet's self-healing capabilities. So looking at the data for the 2,141 bidirectional paths between anchors, in Germany and Finland, we saw that about 30% of paths experienced interdomain changes, meaning that traffic was rerouted through different networks entirely. Nearly 49% saw intra-domain changes, with the rerouting occurring within the same networks, but along different paths. And about 21.5% showed no interdomain or intra-domain changes at all, so the network just kept on running as usual. So the graphs that you see here show the round-trip time increases for each category. Interdomain rerouting saw about 26% of paths, with latency increases over 3 milliseconds. Intradomain saw about 38%, while paths with only circuit-level rerouting saw just 5% with similar increases. I don't know about you, but this is like watching the internet's immune system respond to an injury, and it's quite fascinating if you're into that kind of things. So in conclusion, what can we learn from all this? So internet resilience, which is really important in these times, when we depend so much on the internet, will depend on multiple levels of redundancy. And these redundancy mechanisms provided an effective defense against damage in the seconds following the cable breaks. Building redundancy into networks means embracing a mindset that prioritizes decentralized connectivity, inter-provider transit diversity, having different connections, and interconnection at geographically diverse internet exchange points. And this is a bit like not putting all your eggs in one basket, except the eggs are packets, the baskets are cables, and dropping them doesn't make a mess on your kitchen floor, but rather disrupts critical communications. So maybe not exactly like eggs. Now the story continues to evolve. On January 26th this year, another cable, this one belonging to the Latvia State Radio and Television Center, connecting Sweden and Latvia, was reportedly broken. Our analysis showed packet delays between selected RIPE Atlas anchors increased by 5 to 20 milliseconds at around 0:45 UTC. But again, the absence of packet loss indicates that the internet successfully routed around the damage, like we saw before. If you're interested in further analysis of the cable breaks and internet outages, there's a QR code that you don't have to scan. We've heard you don't have to, but if you do, it'll take you, I swear, to the RIPE Labs article, and otherwise just go to that URL. Now, beyond the Baltic Sea, in other parts of the world, like Taiwan, smaller measurement footprints make it much more trickier to analyze the cable damages, because we can't simply rely on guesswork, right? We don't have the data. So if you're aware of anyone interested in hosting a RIPE Atlas anchor or probe, feel free to reach out to us. More measuring points means more clarity about the global situation of the internet. And on a different note, but also interesting to know, Chile experienced a nationwide power outage on 25 February at around 18 UTC, and our RIPE Atlas anchors there helped us see which paths were affected, who lost connectivity entirely, and who just moved to alternative routes. Through these events, whether cable breaks or the lights going out, we get a window into how networks adapt in real time. And this brings me to the end of this presentation. Luckily, the cables did not break completely. I want to thank you for your attention. If you're curious about learning more or hosting your own anchor to assist in measurements, please reach out to us. And I hope that these insights were valuable and somewhat enlightening, and that it gives you a nice picture of how the internet works. Thank you.
Gerardo, seeing as you didn't write the slides, are you willing to take some questions if there are questions?
I can try, but again, these were made by my colleagues, so if I don't have the answer, I will derive you to them.
Okay,
Please
so
go ahead.
With that caveat, Julia.
Given that you're using RIPE anchors to detect the damage by anchors, Should we perhaps be considering the name of the devices we're using here?
I'll take that on board, but this is a good anchor. It's a stable anchor.
Okay. There's a question in Dimitri in the middle. Hang on, the microphone's going in the other direction.
Yeah, I can come to that direction. I like the anchors, I can move. So you mentioned the quantity of devices used in Lithuania. Well, okay, Baltics is 3 countries, right, kind of. Although we can call Scandinavia Northern Baltics, because it's still the same sea, right? And I'm just curious, what was the number again? You mentioned 5 in Lithuania?
Yes.
Kind of small, isn't it?
5 anchors.
Okay.
Yeah, 5 anchors. But there's a lot more probes
Yeah.
as well distributed. So I don't know if it's a small amount. I think it was enough to be able to make the measurements and see that how the paths changed and the latency measurements.
Oh, sure. And did Latvia and Estonia had enough too? I mean, I don't remember you mentioned the numbers for these 2.
No, because they were not included. So that I cannot answer. I don't know how many are in there.
I see, because LV was Latvian. You know, LV was Latvian television. Although it's not the internet. Okay, thanks. Cool.
Okay. Well, I think...
We can break.
Oh,
the
wow,
close.
sorry, we've got 2 questions on Menti. If you could take 2 more questions.
Sure.
One more question here. Don't do any measurement direct on the cable?
No, I don't think we do, but I do not know that. I don't think we measure directly on the cable. We probably can see the path through the cable up until the break, but when it breaks, then we don't see the cable anymore, right?
Because on high volt DC cables, we are measured all the time. We can even see when somebody is touching the cable.
Yeah, but what we're doing is we're measuring how packets go from anchor to anchor. So
Okay.
we're not really measuring the cable itself.
Okay, good, thanks.
Okay, the questions on Menti when they're racing around the room.
Using RIPE Atlas, can we identify which link segments actually broke, or are we just doing post-mortem analysis?
We did a post-mortem analysis, but I'm thinking that you might be able to set up some kind of monitoring system where you are listening into, for example, a ping stream, and if the ping stream breaks, then you'll know that your connection broke. So yeah, RIPE Atlas might provide you with some kind of tool for network monitoring.
That basically answers the
Okay.
next question as well.
Cool.
Okay, great. So, perfect. Please join me in thanking Gerardo for an excellent presentation. Thank you so much.
Thank you.